Hello again. Another quick little video to talk a little bit about how we derived the momentum impulse equation. So you'll need this to complete the problems on worksheet 1 and in the future. So to get that started, let's take a look at something we already know. F equals ma, which of course is Newton's second law. We covered that during Unit 5. So starting from that, we know that acceleration can be expressed as delta v, the change in velocity of some object, divided by the time it takes for that object to change its velocity. So if we substitute this in for here, we get F equals a times delta v divided by t. So this is a different way of expressing Newton's second law. To simplify this now, if I multiply both sides of this equation by t, I get force times time is equal to m times delta v. So m times delta v, we would recognize that as being the change in momentum, since we know that momentum is equal to mass times velocity. And when an object changes its momentum, it generally doesn't change its mass, it changes its velocity. That we could say that the change in momentum then would be equal to the mass times the change in velocity for the object, and that's what we have right here. So this is something we call impulse, and the letter for impulse is J, and it can have the units of kilogram meter per second or Newton's time second, since we see that force times time would be Newton's time seconds. So that's impulse. And so we get force times time is equal to change in momentum. So let's see how we could use that in a problem. So in your textbook there are some example problems, and I would encourage you to go through those and see what you can find out. But let's do a problem different than that. So let's say we have a car that is traveling down the street, down a highway maybe, and it's moving to the right. And so we're going to say that the mass of this car is 2,000 kilograms, and it is traveling at 25 meters per second. And since we're saying it's going to the right, then we're going to establish to the right as our positive direction. We're going to look at two examples of how this car can stop, and this is very similar to one of their example problems in the book. We're going to say that if they apply the brakes, this car can stop in 4 seconds. Let's say the car can't apply the brakes. Maybe it's icy, whatever. Car hits a tree. In that case, it stops in 0.32 seconds. So 3200ths of a second. Pretty fast. In each case, we want to find the force. So we want to find the stopping force. Okay, so let's take a look first of all at the case that we hope happens, applying the brakes. Okay, so we start with our equation. Force times time equals mass times change in velocity, which is, of course, the change in momentum. And so we know the mass of the car is 2,000 kilograms. We know its final velocity is, of course, 0 because it stopped, and its initial velocity is 25. So force times, and we know the time it takes to stop when it puts on the brakes is 4 seconds. This will equal 2,000 kilograms times the final velocity, which is 0 meters per second, minus the initial velocity, which is 25 meters per second. So, force times 4 seconds is going to equal, now 0 minus 25 is negative 25, and negative 25 times 2,000 is going to be 50,000 kilogram meters per second. But since this is 0 minus 25, this becomes a negative number. So, oops, in my original video, the stuff that came after what I wrote here didn't show on the screen, so I'm just going to insert this little part to show you what happened. So, once we have the force times 4 seconds equals 50,000 kilogram meters per second, we just divide both sides by 4 seconds to find what the force is. So we get 50,000, and this is negative, remember, negative 50,000 kilogram meters per second divided by 4 seconds, and that gives us, for the force, negative 12,500 newtons, which is quite a lot. So let's take a look at the situation with the brakes, or if it hits a tree. We hope it doesn't hit a tree, but we realize that it might. So in this case, the time to stop is 0.32 seconds. So we do it the same way. We start the equation, always start with that. So go to the change in momentum, which would equal mass times the change in velocity. So a couple of things about this. One thing I could do is just divide both sides by t without putting any numbers in there first to get the force. And that would be the mass times the change in velocity divided by the time. So the mass times change in velocity is the same as it was last time. It doesn't matter how long it takes the car to stop, or I'm sorry, it doesn't matter how you stop the car in terms of the fact that you stopped the car. So it went from 25 meters per second to 0. It's the same mass. And so this is still going to be equal to negative 50,000 newtons. And the time in this case is 0.32 seconds. So the force is just going to be equal to 50,000 newtons divided by 0.32 seconds. And this comes out to be, and it's still negative because the change in momentum, the impulse, is negative, 156,250 newtons. And so notice that the force that was required to stop that car became much greater than the force that it took to stop it with the brakes when it hits a tree. And you might expect that. And the reason is not because the momentum difference was any different, because it wasn't. It's because it took so much less time for the car to be stopped by the tree.